So we're going to take on a challenging but central topic within the sphere of dynamic modeling. Arguably, it's the most important topic within the scope of a model's evolution. And it has to do with this issue of model conceptualization and boundary setting. So we had noted earlier the analogy between dynamic models on the one hand and maps on the other. Both of them represent, at some level, a simplification of an extensively rich world. A simplification that of necessity hides details, leaves out details, but brings out salient details. And I argued that which details are brought out and which are left out is a function of the goals of the model, the purpose of the model. Sometimes it's called the problem that you're trying to address. For those from academic or research background, often this is the research question you're trying to answer. In other cases, it may be a broader goal, catalyzing change among a diverse set of stakeholders who are often at loggerheads or what have you. But the fact remains is, for a given situation, we'll build different models depending on what our question is, what we're trying to do with the model. The models look quite different. And I argued that all models like maps are simplifications, and therefore from a kind of shallow perspective, they're wrong. They're incomplete. They leave things out. But that they're useful in large part because they leave things out. Just like a map that leaves things out is necessary to have it fit on your GPS system or fit in your car map folder or what have you. So it is with models. Models can be built realistically, can be calibrated, can be run in a timely fashion, can be understood by virtue of the fact that they are simplifications. And some models, as George Fox observed, are useful. And it's extremely important, for reasons that Ashish had commented on earlier today, to recognize that when it comes to agent-based modeling, while we have tremendous flexibility to represent all sorts of processes, fundamentally, we're going to be on a fool's errand if we try to have a complete representation of a situation. If you try to say, okay, we are going to represent the immune system in all its detail, or we say we're going to represent, the complete criminal justice system of Saskatchewan, all the inmates, all the people in the population who have been inmates, all the staff, and represent it in its totality, we're going to be fooling ourselves. Because of necessity, we're going to need to simplify certain features of it. There's certain things we're going to need to leave out. And establishing a clear purpose of the model, being clear about what you're trying to accomplish with this model, is very important for defining what is included, what is worth including, what is a priority to include. And there's a variety of different purposes that I noted yesterday for dynamic models. One is to explain trends, or as we call them, system dynamics reference modes, sort of, these are patterns of behavior we may have noted, is what you're trying to do to explain some puzzling patterns that have presented themselves across many different data sets, different facets of an underlying situation you're trying to hypothesize about. For example, you're trying to explain the patterns noted in Christakis and Fowler regarding clustering of obesity cases? Or is what you're trying to do trying to understand differential impacts of different policies? Are you trying to rule out certain hypotheses, or just think through the implications of certain processes that are probably interacting. There's many types of goals we could have with the models, and being clear about which are the foremost goals for us is very, very important. This process requires us to think quite explicitly about model boundaries and to realize that adding factors into the model, adding more components in, does not necessarily lead to more insight. Often it's simpler models that give great insight, and there's an opportunity cost. If you add something in, it's going to take time that's going to take away from something else, chances are. It's going to prevent you from looking at something else. Now, the modeling process is an articulated one, and in some other contexts, I've given lectures quite extensively on the stages of agent-based modeling, recognizing, as we'll see, very heavily emphasized shortly, that it's an iterative process. We don't just go through from left to right, sweep through, but rather, as you can see from the arrows, we'll often go back and we'll refine things, we'll learn and we'll add things in, and sometimes we'll take things out or re-aggregate, etc. But broadly, there's some stages here. Problem conceptualization, mapping out the problem. In system dynamics, we use these things called causal loop diagrams, which can be used with agent-based models, but don't really capture the different contexts and different sort of elements of hierarchy between individual level and aggregate quite as well. We have some variants of this that Jeff and I have worked on that are other languages. Model formulation stage, where we go beyond a conceptualization of the model and a map of it to actually having a detailed specification that's runnable of the model logic. That formulation stage is the stage at which the model becomes actionable in terms of running. Model mapping may still be useful to elicit feedback, to compare mental models, but it lacks the precision of the crispness and the exactness of a model that's formulated to run. We can't run a causal loop diagram. We can't run a model map. It can be useful for dialogue as a boundary object, but to run it, we need to proceed to a model formulation stage. And that involves formulation of the structure of the model. Here, what the states are, the transitions, the events associated with it, parameters, etc., and assigning particular values, specific enough we can run it. There's often a stage then of model calibration, which we'll be talking about later in the week, where we're trying to simulate the model over time and the emergent patterns of that model, things that we haven't told the model to represent, but it's showing to us. We haven't told it what what their behavior is over time. Rather, it's telling it to us. We try to match those against emergent patterns we see from the world. Patterns that aren't reducible to any one parameter, any one state. They're rather features of the world that are emergent and that reflect many different factors. And we want what the model produces to match those observations in the world. Often there's a model testing stage. Often that's before model calibration, where you're doing some formal testing with the model. Maybe it's unit-based testing. Maybe you're doing testing for extreme values with the model, etc. And often there's a stage of policy evaluation and knowledge translation. Now, this is a great simplification of the process, but it captures the fact that there's a stage process, and these different processes are seeking to refine our mental models over time. Now, my focus here is on problem conceptualization and a little bit problem mapping. The challenge here with agent-based models is that we have a poverty of riches. These models have a flexibility and a generality that is such that you can create arbitrarily rich models. There's no direct barrier from you adding in more detail, adding in to a person extra levels of physiologic detail or extra levels of detail about behavior or decision making, or about the context in which people are embedded, the physical context, the social context, the resources. You can add these things in, but at what cost, it's not always clear. It's not always clear. And because of this, it's very easy to add deep levels of detail. Yeah, the risk is that more is sometimes less. That adding things in will sometimes preclude, because of the opportunity costs involved, because of the complexities involved, some of the gains you would have had from a somewhat simple model. So, a few general principles. So, as I noted, there exists a high opportunity cost to investing in a given model area. Given the fact you have limited time for this model, often we put effort into one place and it takes away from effort into another place, or effort for learning, running the model to learn from it. To be given insights based on the smaller model, you still might learn insights that might be foregone if you're constantly adding things into it. And so I would argue that, to use John Sturman's term, you want to use model purpose as a logical knife to cut away unnecessary complexity, and start small. There's a principle in software engineering that I teach my students. It's associated with agile software engineering. It's the Yagni principle. You ain't gonna need it, okay? So while we could put things in up front, while we could say, yeah, we could add this, we could add a person's age, we could add their ethnicity, we could add their sex, we could add their income level, we could add their education level, all these marital status, all these different things. We think we might need them. Well, wait until you actually need them from the perspective of the clients you're working with, the stakeholders. Don't add them in up front, thinking speculatively we're going to need this. This is a big issue we got to watch out for those of us in the health sciences. Because in the health sciences, as we know, in stepwise regression techniques or other epidemiological investigations, it's very common you'll have a laundry list of different items of data that you've collected, different covariates that you're seeking to try to understand, and you might do a stepwise procedure to figure out which will make it into your model. But fundamentally, you're starting with a big list of characteristics, say, of a person. Now, you're not representing certain things, like their behavior over time and interactions with the environment, but it's tempting for those of us who spend a lot of time reading epidemiological literature to just say, oh, a person. They need, age, sex, ethnicity, social status, etc. And because we can represent them, we need to represent them, and somehow we're going to be better off because of that. There may be a time where your model includes many of those things, but you want the model that gets to that point to be guided by the learning along the way, not to presuppose it's needed up front, because it'll be easier to learn in an incremental fashion. If you add all those things into your model, you may only discover that the model is grown so complex it's hard to understand. It's not as hard as the world quite, but it's slow and unwieldy, and it's not clear what's generating what, and maybe it has bugs in it that you're not spotting, and it starts to become clouded. So the principle here is, maybe you're going to work towards a really rich model, but start simple and add as one develops confidence and understanding about the model. Confidence that it seems to be running properly, there's no obvious misbehaviors. You see behavior, you have a good sense maybe where that's coming from, and you add one thing in at a time. It's incremental model development. Much as the revolution that's taken the software world by storm in terms of incremental software development, I would argue incremental model development is central to success in many modeling projects. And what you heard Wade talk about last time is last night, for example, is a unassuming example of incremental model development. He would add things in, he'd take it for stakeholder feedback, get feedback on it, add additional things in. And there's many advantages to this. And the advantages are not obvious. And in fact, they're very little talked about. I'm probably one of the very few people in the world on the modeling front who talks enough about, no intervention, roughly 5 to 10 seconds. So I'm one of the few people who talks about this virtue of incremental model development. It's probably because I also have been and continue to teach professional software development, where this is part of the course. And not only do you have those motivations for this, because models are, after all, a computational artifact, but you further have extra motivations associated with learning. So the idea here is that, look, with each iteration, the model is modified in some small fashion. And often you'll compare, okay, the new version, how does its behavior compare to what I saw with the last one? And you recognize perhaps some differences. Maybe when the changes you've made, you disable them. You disable a parameter, for example, and you see, okay, does it produce the same basic output as last time, as a sanity check? We'll sometimes do that. And then sometimes, you enable the new changes and you see some new behavior emerge and you have some idea where that came from. And often you'll see whispers of that behavior in the model down the road where this is just one of several features in there, because you'll see them coming through at certain times. Commonly with models, the model's greater than the sum of the parts, but the parts have indications that give rise to behavior you'll sometimes recognize. Now, one of the big virtues here is these incremental versions can be demonstrated to others. So we always have something in hand. Jeff put it this way, and Wade echoed it from Jeff. Always be half an hour away from a running model, right? For a model you could show to a stakeholder, or from some model that is runnable and can be demonstrated. And often these incremental models produce behavior that might help motivate the decision where to go next. But often, as in software, it's an amazing thing. I never would have guessed it as a young man. But it's often not till we see something that our thoughts about it can be clarified. And once we actually see it, we can have much better understanding of what we want to see next, or what needs to be changed. You might think, we can just keep in our heads. We know what we're going to see. But it turns out there's something about the limitations of human cognition that when you see something and encounter it, particularly something where it might exhibit behavior you didn't expect, it elicits a new understanding that might say, well, look, let's take a step back and look at this thing. Or, we added that in, let's take it out for now, or let's aggregate it out for now, or assume a uniform value for that parameter for now, and take a somewhat different tack. You become more savvy. You become more savvy through learning from the model. So a few benefits from incremental development. Developing it one step at a time. Even if you know this is not the final step you're going to be taking, putting something in, building, running, observing the results, adding things in. You notice how that's we've been doing things, these successive versions, and it's not an accident. You have a greater understanding for modern patterns emerge and their interactions. So maybe your model has many things in it, but because you built it up step by step, you have some sense about where the patterns you see out of the model come from. A colleague of mine who did agent-based modeling for her PhD tells me a sobering story. So she did this at a large American university that will remain nameless, and she built a model for tuberculosis in an agent-based way. It's actually interactions of tuberculosis and smoking, and it was an agent-based model, and it had lots of factors in it. It was really, really rich. It had social networks, it had aspects of differential smoking behavior, it had, quitting and continuing to smoke, but it also had perhaps other types of tobacco and a wide variety of things. And she found she would run this model and she'd see really interesting behavior, but she didn't know where it was coming from, why she was seeing it. And not being a computer scientist, it was hard for her to dig in to even, was this model running correctly? Maybe she was seeing really weird behavior because it was a bug, not because it was emergent patterns. This is a disconcerting feature. We see surprising behavior. When we see surprising behavior for software systems, often we think there's something wrong. When we see surprising behavior for these models, we don't know if it's something wrong or something great. Something really interesting. We're learning from the model, and that's disconcerting. And she ended up struggling with this for a while, struggling to learn from the model, to learn something coherent, to sharpen her understanding. And she ended up actually putting it aside and using a much, much, much simpler model, because she felt at least she could learn in a more confident way from a far simpler model than from this kitchen sink model. And that's a parable for all of us, because the impulse is there to add, but there's got to be that reflective process along the way at the least. So when you build it up incrementally, which she didn't do, you learn along the way and you see where these patterns come from, and hopefully you take notes on it, so that when you do see them in a more complete model, you have a sense of where they came from. Critically, you can change direction based on the learning. So maybe you get to that bigger, better model, but you get to a much more savvy, bigger, better model because you've learned along the way. You've learned what's really important, what's really sensitive to. Some of these things you can't tell ahead of time. Models can be wildly sensitive to certain parameters and terribly insensitive to others. You vary a parameter by a factor of 10%. Certain parameters may make a big difference and certain very little at all. Almost no difference. And that may strengthen the impulse to put effort into the things it's really sensitive to, the things that seem to have a big bearing on sort of trade-off between interventions. Another thing, critically, absolutely critical to learning is you secure feedback from stakeholders. You show it to them and they tell you something. Maybe they say, well, that's not so interesting to us, but we really want you to put more effort into this. Or if you could bring that out more, get more detail in that, show even some additional levels of detail, maybe we could help you, help guide you better with respect to this area. So, for example, sometimes the stakeholders may see patterns coming out of the model and say, that's plausible, that's similar to what I see, or that's similar to what I used to see 20 years ago, but I never see that now ever since we added triage unit in. Or they may end up saying that's completely different from what I see. Again, that's not a failure of the model. It's a success of modeling, because that understanding that what you've represented in the model is not representative of a plausible representation of the system. You wouldn't have known that except if the model shows you what logically results, the output of the model, and then you show it to a stakeholder and you get that feedback. So getting that feedback from stakeholders, either on model structure or on model output, is really valuable, and to get it on an ongoing basis. You also see what excites them, what speaks to their needs, what they say, yeah, I'm really interested in that. That's useful because then you spend your time and prioritizing things that are more likely to yield stakeholder interest. So you have greater clarity and prioritization from the above as well. You also have a faster ability to diagnose bugs with models, to diagnose what might be going on. You add just a little bit and something goes wonky, something goes awry. Well, the problems can only lie in so many things. You just added a small thing. Something about what you did brought out that problem. Often it introduced the problem, sometimes it manifested a pre-existing problem. But you can more quickly track down where the problem is. If you add a whole swack of things for a month, and then run the model and it doesn't work, who knows what you added caused or manifested the problem. But if you add just a little bit and run it, your problems will be more clear. And they'll be more manageable. There'll be fewer error messages, etc. related to what Ashish talked about yesterday, this notion of time boxing. We only have so much time for this model. Trying to get it done. Well, with incremental development, at least you always have something in hand. You have the last model version. So if you get sick, time is cut short, you run into some really arcane technical issue and Wade's not around or what have you, Winchell is in short evidence, at least you have something in hand you can show. You've got something to show. Whereas if you don't have that, if you build the bigger, better model and you say, we'll deliver it 6 months from now, maybe it ends up taking a year. Maybe it ends up taking 2 years and you don't have it in hand. You get stakeholder confidence because they're seeing the model come along. Maybe there's a sense of buy-in, a sense of ownership from them because they've given feedback many times. And improved morale on the part of the modeling team as well. Okay, this is going places. So one of the big things we do in software development, we produce these successive versions. You can show them to stakeholders. The model team has a sense, okay, things are cooking. We're moving along here. And often in software development, this is something I didn't emphasize, but in software development, like modeling, it's notoriously difficult to estimate how long it will take to do a big chunk of work. It's horrible. Software engineers are terrible about it. When I was at MIT as an undergraduate in the late 80s, the joke was that for software projects, to get a good estimate of how long it is, and I'm not sure I have all the details right after all these years, but it was something like you take the estimate, you multiply it by 7, you add 1, and you shift it up to the next higher units. So if they say it's going to take 3 hours, multiply it by 7, right? 21 hours, add 1, 22 hours, and it goes from hours to days. And that'll give you some sense. So the truth is, as software engineers, when we think about big chunks of work, we're very poor about estimating. But if you think about a small chunk of work, you start thinking in very concrete terms. I probably chose the wrong one with hours, but it's much more problematic if you're estimating things in months. I think it will take 2 months. It's much more problematic. If you've only got, if you're thinking about things that have a delivery time within a week's time, you start thinking in concrete terms. Okay, I'm out of the office on this day. So-and-so's sick. I've got this competing deadline. And you start being very concrete about what can I get done in that time. And you start thinking about very specific things you got to do. Okay, there's an uncertainty about that, and uncertainty about that. And you give a range estimate, best case, worst case. And you can do far, far better with short chunks of work. And so often you can end up having a sprint that's a week long or at most a couple weeks long and be quite on the ball about how long things will take and do it in a time-boxed way. Time-boxing means you only have X amount of time and you need something to show during that time to deliver. Okay, incremental model development. How do you choose how much to put in the model and what to leave out? Well, there's a variety of factors that we consider that come in there. This is actually a slide that came out of a somewhat unsatisfying consensus discussion with some other modelers. I'm actually not very satisfied with this slide, but it gives some ideas. What do we need to capture, if we're interested in key interventions, we have to understand the effects of a certain intervention. Then somehow the model has to characterize the types of things modified by that intervention. If we want to find the effects on HIV incidence of handing out needles, we need to represent something about needle use, and we need to represent probably something about needle sharing because the fact that people share needles that can spread HIV that's reduced by needle distribution. So we need a model with some sort of characterization of needle sharing behavior among intravenous drug users. In this case, we're thinking needle sharing among IDUs. So here, if we want to evaluate that intervention, we need a model that's at the requisite level of specificity that it can deal with those things. And you know, there are many types of interventions out there you might be interested in. Oh. Okay. 2 seconds or 3 seconds? Yeah. Cool. Thank you. Thank you. This is awesome. Is there data available at a particular level of analysis or granularity? This sometimes comes up. I mean, there are times where you want to build a model that's fairly empirically grounded, but there's just no understanding of phenomena at, say, an individual level. But there is information at an aggregate level concerning behavior. Sometimes this will lead you to say, okay, let's keep the model characterization at more of an aggregate level for this analysis. Similarly, if there's theory at a particular level, but not at another, that's an important consideration. For example, there may be theory about why a system behaves a certain way it does at an individual level, but not at an aggregate level. And an agent-based model can be a very suitable tool for that, because the model explicates theory at an individual level and sees its implications for aggregate behavior. To what degree, okay, so is heterogeneity key for understanding the process or problem? You know, are there features of the situation in terms of disparities? You want to capture disparities in outcomes between the outcomes for lower income and higher income individuals. If you want to do that, your model needs some representation of high and low income or income at some level, or else you're not going to be able to capture that difference. The model needs to be able to distinguish people, you know, of different sorts. Or, you know, is heterogeneity important for intervention delivery? You want to intervene on individuals who are repeat care seekers in an STI clinic. Okay, we got to represent something about someone's STI history, presumably, in order to capture this. Maybe there's heterogeneity that you're looking at in network connections. We want to look at the core members of a network. Well, probably a random mixing model where we just assume people mix all across the population with equal likelihood is just not going to cut it. We need to have a representation of you know, people's position in a social network or in a contact network. There's another issue too, which is how do stakeholders conceptualize the problem? Jeff talks about certain encounters with stakeholders where one level of characterization of a model just goes way over their heads. I've met some people who feel much more comfortable with an agent-based characterization than they do with a aggregate characterization where people are put into different categories as a count of people. They find they can relate to an individual level characterization better. Jeff talks about clinicians being in this category sometimes because their whole life is centered around individual interactions, and you know, understanding a model where you're depicting individuals rather than abstract categories of individual is more straightforward. By contrast, I've met demographers who are just much more comfortable with an aggregate characterization. They're used to stratified characterizations of the population into counted categories, and an individual-based model doesn't really float their boat that much. It's okay, but they feel very comfortable at the aggregate level. Okay, a key factor that you need to think about when shaping your model at each stage of the process, and your first thing is, okay, for this next stage, What's going to be endogenous? Which things are the model going to generate for us? It produces them for us. What things are, by contrast, exogenous? Things that are told to the model, pre-specified to the model, and just assumed by the model. Maybe they affect things, but they're in a pre-specified way, and excluded or ignored. So, with each of these models that we've explored here together, we should be able to calculate. So I'd like to go through a little exercise. Let's go take a trip down memory lane. Okay, so ladies and gentlemen, which features here would you say are endogenous within this model? So this is our little model of spread of infection. Which things are being generated by the model over time? Give me one.
Recovery?
Yeah, so recovery. And in general, people's infection status, it's changing over time. The model's generating a depiction of, okay, how many people, for example, are infectious or recovered or susceptible, etc. It's generating that. We can't tell it, except at the initial state, we can tell it, okay, people are starting in these states. After that, it tells us. It's producing how many people there. So that's good. What things are we sort of specifying to the model? The model's not generating them over time, but they're fundamental things that are shaping this model. Yeah, the population size, and in fact, the network structure. Now, you could say, well, wait a minute. The model's generating the network structure. Okay, at the initial time, the model's generating the network structure. That's true, and I won't quibble with that. But basically, the model's not over time generating changes in network structure. Right? It's not like over time people see their neighbors infected and they grow anxious and they cut some of those connections, as that work by Hammond and Epstein on the dual contagion of fear and pathogen posits. It's not that the network is being generated over time. It is being generated at the initial time. But I could just as well load in a fixed network into this and say, go figure. Here's a network, go assume it. In fact, for some of our work, responsive to the question from Claire earlier, for some of our work, we have sort of imposed a pre-specified network. So we have networks, for example, gathered by smartphone contact pattern data, where we know for a given group, at certain periods of time, A and B were connected and not at other periods of time. And we feed it into any logic, and we see the consequential patterns of infection, which we didn't observe, spread over that network. That's pre-specified. It's rich. The model's considering it, but the model's not generating it. It's being specified to the model, albeit in a rich form over time, but it is pre-specified. Here, the model code is, there's some generation of the network at the beginning time, but after that it's really a fixed thing. It's given to the model at the initial time, and from then on it propagates. There's some other things here. For example, recovery time is not endogenous. It's fixed. We have a fixed mean duration of infection, duration of immunity. You could imagine a model which has what types of things might plausibly, within the sphere of our health experience, affect recovery time. Think from STIs, for example. Is there something that might affect the time to recovery? Treatment. Yeah, you treat people with antimicrobials in response to STIs. So gonorrhea, chlamydia, these bacterial STIs, you might treat them. And that might actually change the recovery time. Now, you might have some people that present for care, some people are asymptomatic and don't present for care, and you can enrich it there, but have separate exogenous treatment times, specified. You might also imagine an individual, for example, growing concerned about other individuals getting infected in their sexual network, being more likely to seek care, and therefore having a lower treatment time, a lower time to recovery, because they've sought treatment and they get treated sooner. So there would be endogenized. What's given just as a fixed assumption for a given run of a model, we could actually have modified based on people's behavior for some models. And a model like that would be working towards a more endogenous theory of time to recover from infection. I'm going to open a few more models with which we've enjoyed the pleasure of acquaintance. At least it has been a pleasure for me. Our model last night is not a good example, but I will load one that we had opened yesterday, and we had downloaded it here. So this was this model of the GIS and in food environment. So this one we talked about in passing. This is this model of the model of the fair city of Melbourne. Thank you. 2 second down. Now, is it affecting those screens?
It was just the center one again.
Okay, awesome. This is great. We should get the, sorry. So the reason it's great, sorry, this is the software engineer and debugger in me. If I want to fix an issue, I want to see the issue so I can fix it. I want to see it with enough regularity that I have a chance of diagnosing it. And now is the time to summon those who can debug this, other than myself. So, ladies and gentlemen, here we have a model of Melbourne. And you may remember that we had people, we had people in here, and I'll do it full screen, and decision making, etc. What things within this model are endogenous? What things are generated by this model over time? I'll give you a hint. This is a stock and flow model of weight. It's building up, it's decreasing, so energy comes in, energy goes out through basal metabolism and through physical activity. So weight is in fact endogenous. It's changing over time in an endogenous fashion. What else is endogenous? Energy expenditure, good. What they eat is in fact endogenous. They're making decisions in this model about what to eat. We're not pre-specifying this agent on this day consumes 6 boxes of Tim Tams. Tim Tams? This other one eats only lettuce. This third one exhibits an inordinate, voracious appetite for meat pies. We're not forcing that over time on agents, as colorful as it is to imagine. Rather, we are characterizing over time decision-making on the part of the agent and food-seeking behavior that is probabilistic and reflects their distance to the supermarket, their distance to a convenience store, their distance and their preferences. That considers those preferences and routes them to shopping for a supermarket, which does the general larders fill, to abuse Julius Caesar, or it routes them to a convenience store where they enjoy the company of Twinkies and floaties. So this is endogenous. Their food shopping behavior is endogenized. There's some other elements that are endogenous here, elements in their variables, like how many meals they have at any one time that are from the supermarket or from the convenience store. What things are specified as fixed to this model? Anyone?
Distance to birth.
Yeah. So really, we generate for this model their home locations. So you could say that there's only weakly endogenous. I mean, at the initial time, we assume them, and it's not quite pre-specified by us, just like in that previous model. We didn't exactly specify the network, but we specified its parameters, and then it generated for us. But then the distance to convenience stores, or distance to parks, or distance to supermarkets, those resources are all fixed. The nature of those convenience stores and supermarkets and parks are fixed, with the exception that I did modify this model the night before the boot camp to add supermarkets in dynamically. So when you click on the model, I add them in. But even that is not endogenous. Why? Because I'm specifying it external to the model. The model's not generating supermarkets. If this model had noticed, okay, there's few supermarkets in this area, but there's an unusually high demand, now we'll build a supermarket based on that. Or, if it shaped the availability of healthy foods within convenience stores based on food-seeking patterns, then it would have endogenized some features of that. But for right now, the location and nature of those resources are fixed within the small. It's rich. It considers them. It considers supermarket location and convenience store location and street routing, all that sort of stuff. It's great. But it's not endogenous. They're not laying down a new street on its way to, this supermarket because of the need for that, or adding parks because, a better example would be, they're not adding parks because the population's growing obese. They're not changing the rules for what supermarkets can stock based on obesity patterns in this model. Yes, Ashish?
Is it reasonable to think of exogenous as that which existed before you started running the model?
I mean, loosely, yes. It's really the things that are pre-specified to the model. In other words, it's things that are often pre-existing, but basically, while the model's running, it's already dictated at the very start of the model. Essentially, it's the die has been cast. You know what the situation is, and in that sense, like the networks that are generated at the very start, I would count them as kind of, in a way, they're exogenous. They're not including elements generated by the model over time, if that's helpful. It's not generating it over time. Yes, it generates it at first, but that's kind of a static specification of it. You'll notice, by the way, in case you didn't run it long enough, the size of these agents reflects weight issues, and so actually the visual representation does convey some of the underlying endogeneity of weight. We had a previous version of this model in Saskatoon being demonstrated not 4 years. This one seems to be sort of flexing some, and people became large discs of wide dimension and small height. Yeah. So this is a model that has some features that are specified to it that have a very large impact on the model. I'd like to actually download that model. For some reason, I don't have it present, but there was a model, models built-in class preview day 1. There's this model from Sydney. You may remember that. I'm going to download it here. I'm surprised I don't have it already ready for opening, but here it is. So what's endogenous? You may remember the Sydney model. It was kind of the exemplar for us to build our model of smoking last night. What features here are endogenous? What does it generate?
state of smoking.
Yeah, good. Yeah, that's right. At an individual level, whether each person is smoking, in fact, at a population level, how many of people are smoking, etc. So that's good. Other things. Look at the vital processes. Is the population size fixed here? No. Those other models we looked at, there's a fixed population size. We pre-specified. Here, is it fixed? No. We have death and we have birth, conception going on. What other things are endogenized here? Well, development of disease. And in fact, disease affects death risk, as I recall. It affects the hazard rate associated with death. Even behavior and motivation changes over time endogenously. Motivation to make change in habits. Care seeking is represented explicitly. People seeking care in neighborhood clinics and so on. We're characterizing over time features of that. Here, death rates are as I recall, endogenized. So they're being affected by characteristics of that agent that are themselves endogenous. So someone's chance of death per year is not a hard-coded, pre-specified thing. It depends on the presence of heart disease, for example. And both diagnosed and undiagnosed differentially. So managed heart disease has lower risk. We also have risk from smoking, that's from current smoking, for example, and that we have some age-specific risk. So here, rather than just dealing with an age-specific death rate, which is pre-specified, we're actually having a death rate which is endogenized. The model produces this death rate. What things, by contrast, are exogenous here? Is there something exogenous? Well, as in the other model, the answer is yes. The location of these clinics, I believe, is based on GIS data for the city of Sydney. The nature of the physical environment, its connectivity, is based on pre-specified factors. And there's a whole swack of factors relating, for example, to fertility that are exogenous. There's factors related to, I think, smoking rate. Smoking rate is, what do you think? Here's a formula for smoking rate. Do you think that's endogenous or exogenous? Well, it turns out it depends on the person's SES, so that may be pre-specified. It depends on the count of their connections in their social network that are smoking connections. Does that sound endogenized or exogenized? It's endogenized. One person, if you can get one person to quit, it will make their friends more likely to quit. They are shaped by the smoking status of those around them, and that smoking status is itself endogenous. You'll get clusters of smokers because their smoking habit will be, if not encouraged, at least made less unwelcome by their surrounds. In utero exposure to smoking is also considered. That is an endogenous feature. The model's generating it. Sometimes the women, when they're pregnant, the expectant mothers will be smokers, and that will put the baby at risk of developing smoking habit themselves, initiating smoking. So in short, there's many aspects of initiation that are smoking and that are endogenous. Quitting is based on a motivational coefficient, that's endogenous. Relapse rate is based on a relapse motivation component. There's a lot of things in here that are in fact endogenous. The chance of developing heart disease depends on smoking, but as we said, for fertility rate by age, that's fixed. So some things exogenous. This model has a lot endogenized. involving these factors. Okay, so we've gone through a couple examples there, endogenous, exogenous, and then there are some things which we didn't comment on because they were left out of the model altogether. The model excluded them. Not that they are definitely not important, but they're not part of our thinking exercise right now. We may add them in later, but for now, they're part. So why include something as endogenous, for example? Well, if there's key dynamics you really can't capture without, this is just to include a variable in the model at all. If you can't capture key dynamic behaviors without this thing, that's often a motivator to put in. You need to capture the effect of an intervention, maybe a targeted intervention that keys off the person's sex or number of times they've been to the clinic. You're concerned about how it will be affected by an intervention. Maybe that would be a good reason to capture things. Or about how it's associated with an intervention outcome. So you want to track, for example, how an intervention affects different groups. Maybe you want to compare the model output with observed data, with empirical data. And by representing this in the model, you're going to be able to compare the model-generated data with what comparable data shows from the world. That's an attraction for representing it. Or if it's somehow very important for stakeholder credibility. These are some reasons to include it for certain types of models. They apply less to other models that are thinking models, where you're not specifically seeking to understand the effect of an intervention, but rather to think through some interactions. So why include things as endogenous? This last slide is why include them at all. Why include them as endogenous? Well, capturing as endogenous can lend extra flexibility for capturing effects of interventions, for example. So that model we just saw, this model here, the fact that we have made, for example, heart disease, its incidence rate depends on smoking, allows us to capture in this model the impact of interventions to lower smoking burden on its impact on heart disease. If we had hard-coded this, people just develop heart disease at a certain rate, it wouldn't matter how much we got people to quit smoking, it wouldn't impact the development of heart disease. Similarly, if we didn't capture the impact of heart disease on death, we wouldn't be capturing the impact of changes in management of heart disease, for example, diagnosing more people, on population mortality. And by extension, we wouldn't be capturing the impact of smoking through heart disease on mortality. Because after all, if we have A affecting B, if we have smoking affecting heart disease, and we have heart disease affecting death, then we have transitively, by transitive closure, we have smoking affecting risk of death. And by capturing those linkages endogenously, we could capture the effects of, say, smoking interventions, right? We might also capture the effects of motivational factors here. Motivational factors that help people quit smoking. So motivational interviewing or other techniques that might help in a clinical encounter enhance the chance of quitting smoking through their focus on motivation. So in short, endogenous things do sometimes allow us to investigate additional interventions. Maybe we want greater robustness in the context of change. We want the model to be more robust, say, for populations with different smoking rates. If we don't have smoking represented, how are we going to capture the differential impact on death of different smoking rates in different contexts? If we do represent smoking, we can capture that, and therefore can support translation to different contexts. One of the challenges is extra endogeneity requires more data and certainly more implementation work, and sometimes is a challenge for understanding. But it can allow our models to be translated into context and ask questions about novel portfolios. So I'd like to highlight for you the fact that we have within the agent-based or individual level modeling space, a wide variety of type of levels of intervention, or sorry, types of models. I'm going to put this out here so it will capture me by the screen. Okay, so on the minimally endogenous front, there's a set of simulation models that are called, whoa, sorry, I'm on the wrong screen. I focused it on the wrong screen, man. That are called microsimulation models. And these microsimulation models are very popular for certain types of government policy studies. For example, studying the effects of pension plans, etc. But they really deal with observables. They don't deal with latent factors typically. They deal mostly with observables, and the relationships between observables tend to be hard-coded. The impacts of interventions on these observables are often somewhat more hard-coded and often affect things immediately. It reflects a very particular context, and the model here is a little bit more of a bookkeeping model. By contrast, there's heavily endogenous models, which focus on the underlying causal pathways, where there are a fair number of things that are latent. We can't observe directly, but we posit there's that going on. We may not have empirical data, for example, that's really good on the motivation or the number of individuals who are former smokers. This is not a good example in a population. Or factors regarding asymptomatic individuals, but we represent them not because we have data on them, but because they're important for characterizing the situation. For example, individuals who have asymptomatic infection with gonorrhea may be an important reservoir of infection for those who do develop gonorrhea separately in a symptomatic way. Here, between observables, we're mediated by pathways. The pathways posit certain underlying sets of interaction. And the effects of the intervention on the observable are mediated by these pathways, these causal pathways captured in the model. And disparities are often captured by contextual differences in a small number of underlying parameters. You're not hard-coding that this certain group has lower rates than this group. Rather, those result from differential, say, in terms of SES or education level or what have you. And the model captures an underlying theory. These are two extremes of models that you'll sometimes see. And I'll contrast that with another spectrum, which I will use in terms of model purpose. And in the ABM literature, in the individual-based modeling literature, you will see both examples very strongly. Man, I should create quadrants with this. There's 3 quadrants that are well represented here in terms of what the purpose of the model is and how endogenous it is. There's a set of theory building models that the term that Carl Simon uses, which I rather like, Carl Simon being now a retired professor at University of Michigan, who for many years was in charge of their Michigan Center for Complex Systems. These are caricatures. We look to a political cartoon, not for exact accuracy in terms of how it represents an individual, but it brings out certain features. So, there'll be a person with big ears sticking out, and you're supposed to recognize George Bush or something. Or, with a big chin of a certain Canadian prime minister. It'll bring out a jaw of someone. And it's not an exact depiction of the person, but it points, as Carl says, to some underlying truth, to some underlying feature of the situation and brings it out. And here, these models are often focused on sharpening thinking. Sometimes they don't depict what we think are, in fact, all the real-world processes operating. We just boil it down to, say, 2. If we have these 2 processes interacting, what would be the impact on model behavior? I gave the example yesterday of segregation, a segregation model, where we boil it down to neighborhood selection. A person moves to neighborhood. that they feel more comfortable in, where their satisfaction is tied to their similarity to people around them. That's probably a grossly simplified version of what goes on in reality, where we know a number of other processes take place. But it suggests a certain generative explanation that by Occam's razor has a certain attraction for why we see certain patterns, or one of the reasons we can see certain patterns. And often these models, as I noted yesterday, have little empirical data that they incorporate. They're thinking tools, and often it's because we don't privilege one set of parameters. We vary the parameters over a wide set, and we try to learn, gosh, when this parameter is high, we see these outputs. When these other parameters are high, we see those. Hey, let's open up one of these models. Can we open it up? Hearing no objection. Oh, okay. So, ladies and gentlemen, let's get some action going on here. Okay, I'd like you to go to help. I'd like you to go to example models. Let's open up the Schelling segregation model, which is the focus of my attention here. So Schelling segregation. I actually have one that I think is implemented a little bit more nicely in continuous time, which you can find in the example models I've provided you. But let's run this one. So how did I do that? I went any logic help. Oh, not any logic help. Sorry. Any logic example models. Help, example models. And I scrolled down in this list here to get Schelling segregation. This was named after the Nobel Prize winning economist Thomas Schelling. Thomas Schelling in the 1970s was interested in the phenomena of segregation and the emergence of segregation in cities in the U.S., which was his home and native land. And he was interested in spatial sorting and spatial processes. And he started wondering, if we just had this process of discomfort with neighbors or desire to be with people like us a little bit more strongly, maybe just a little bit, and we had people who could move, how might that affect things? So he actually used a checkerboard. This is the 1970s. He didn't have access to a lot of computers. He used board that's used for checkers or chess. I think it was the checkers one. And he used pennies. And he put the pennies, I think, head or tail up to represent the different types of people on it. And he would move people around. And there could be an empty space where the penny was missing. And these days, of course, we can run this much more efficiently on a digital computer. Okay? This is much more transparently characterized in mine, in the model that I have. And you could see a publication associated with it. Okay, ladies and gentlemen, here we have a model running, and I'm going to use this little thing to pull down time scale, and I'm going to run this model as quickly as I can. And what you see is pattern. Each little square here represents, for black or red, a person. And the ones that are, khaki color, light yellow, those are empty, okay? Each person at a given time is at a certain location. And by virtue of being at that location, they're surrounded on their different sides by people who might be of the same or a different color or with no neighbors at all. And a person has a certain preference, as indicated by the slider, for people of their same color. And one of the discoveries that Schelling made, you can only imagine how long this might take on a checkers board, is that patterns emerge over time from this that were put in. So I would remind you that when we started this, I'll get it out of this mode and switch it to this. This looked inchoate. Things are scattered down randomly. But people are moving. They're moving, and they're moving in a way with slight bias towards people of their kind. And you can see over time some sort of patterns emerging from the miasma, from the magma, right? And those patterns actually eventually settle down. And they settle down to look distressingly like patterns of residential segregation in certain areas, where you get these groupings of black individuals surrounded by black, red surrounded by red, and these sort of peripheries. And you get this sorting by race that's pronounced, even though it's a fairly modest difference. Now, the interesting thing is here, not having to work with a checkerboard, we can, in fact, I'm going to reset this to time. How did I get that time control? I went down here with this little left-right arrow, and I did time scale. I chose time scale. Okay, here we go. Boom, boom, boom. I'm going to shift it to a lower preference. Okay. So here we go. I'm going to shift it to a low preference, and I'm going to run it out. And people are perfectly satisfied with this much more dappled thing. Again, harking back to Gerard Manley Hopkins. So here we have at lower levels of preference. Okay, this is taking a while to finish. Not sure why. At lower levels of preference, people are often quite satisfied where they are. They're not sorting intensively, and yet, as they grow to higher levels of preference for people like them, patterns will start to emerge. And in fact, there are phase changes associated with this. Whereas you ratchet it up, you'll see differential patterns. Here, for example, there's connectivity. There's interspersion. These things sort of meander amongst each other, and it's reticulated. You do it further up yet, and you can get broad patterns that are coarser in character, that are more conveyed. And at some point, people become so dissatisfied they just circulate and circulate and circulate. They're searching for their perfect home, and by the time they end up moving there, others move out, etc., and it just circulates without end. So this, ladies and gentlemen, is a stylized model. It's a theory building model. It's not an attempt to characterize even a working hypothesis for what's going on, but it helps us think through, if we had those simple situations, how would it affect things? How would it affect the patterns that we see emerge from this model? Those are emergent patterns. We didn't program them into the model. We didn't pre-specify them. They emerged from the model, much like those associations in that first model we ran. And these models help us understand how certain process assumptions give rise to these observed patterns. By contrast, a wide variety of models out there in health are, I will say there's lots of models like this that have emerged in health. Some of Ross Hammond's stuff, for example, on obesity, where you have individuals wandering through fields of broccoli and chocolate cake and eating foods that are similar to foods they grew up with. Those are theory-building models. They're caricature models. Ross does not, I can assure you, having co-taught with him, Ross is not fooled by the thought that Canada is paved with broccoli and chocolate cake, nor that Saskatoon's avenues are lined with such delicacies. But rather, it was a model to think through the interactions of how early life experiences might shape dietary habits, for example, later in life. By contrast, there's a lot of models that are focused on theory explication. You have a theory, and you try to understand what its implication is. You have enough of a confidence about a theory, or you have some stake in the ground. You think is plausible enough, it's worth advancing to investigate consequences. And here you've often represented real-world processes of some sort. You think you have enough to give a decent characterization of the situation for relevance, and you're attempting to achieve many outcomes. It's not just for learning, but often you benefit from learning. But maybe you want to understand the effects on intervention trade-offs. On the cost side, on the health burden side, on the side of cost effectiveness, et cetera. So here, theory explication models take a theory that's already been crafted, which you have some confidence in, maybe through experimentation with models, and try to understand what it would imply, say, about intervention trade-offs, about prioritization of data collection, or about interpretation of empirical data, et cetera. And often almost invariably, these capture empirical data. You want to inform them with a lot of empirical data so that when you explicate the theory, it's with good contextual information where possible. So these are two different spectrum. The interesting thing is theory explication models are sometimes seen to a degree in a minimally endogenous form and a heavily endogenous form. But theory building models are typically going to be more endogenous and less exogenous. I could go through some examples here, but I think I'll just leave them in the slides because I think we did some justice to it with the models that we looked at in terms of exogenous and endogenous features. What I will say is, as Jeff says, each one needs to take their own journey. And there's a learning journey associated with this. And your model may end up with more endogenous features because you're taking on more ambitious challenges which encourage you to put in endogenous features. Or maybe you're putting an emphasis on understanding certain results and you go lighter on putting in endogeneity early on. You have just a few endogenous features to maximize the learning. We often learn more effectively. Kierkegaard said, I think it was, that the tragedy of life is that we learn backwards, but we live it forwards, right? And with models, one of the tragedies is, I don't know if it's a tragedy, but it's a tension, that you learn more easily from simpler models, but you actually often are more interested for the goals of your model in more articulated models. And one way to try to navigate that tension is to build the models incrementally, to add a piece at the time and learn from each piece as it's added. And that can give you a model that you're going to that's richer, but at the same time one you've been able to learn from, because you've been observing it at each point along the way. It's a shame, but these sort of comments are just not available in the ABM literature. In the system dynamics literature, you'll see hints of this, but the whole idea of incremental model building, it's hinted at some places. There's a book by Rob Axtell, and I think Epstein may have been involved, but it's an edited volume which has a little bit of model docking. But this idea of step-by-step model execution, so I mean, it's one it's largely favored by my software engineering backgrounds, but there's just not a lot of talk about these principles. And in general, I'll say this. If I were to critique the ABM literature in contrast to the SD literature, and I know both well, and I know both communities well, the system dynamics field tends to be more introspective. It tends to be more reflective on its processes and the human processes, the human feature of modeling, than the ABM literature. The ABM literature tends to be less focused on how we build models and more focused on what we get out of them. I personally view the modeling process as major learning opportunity as the model that comes out of it. And if I had to choose between the virtues of modeling versus the models of having a model, I'd choose the virtues of modeling in a heartbeat rather than the model that comes out of it. But in ABM, it tends not to be talked about as much. And Jeff has alluded to some work in the system dynamics area where it's talked about more. So, I've provided some examples here of additional thoughts. But those are some thoughts that I had on ABM conceptualization. And the most important question is, what are you trying to get out of the model, and what needs to be in it to get that? If you're trying to learn about a few basic things, you want to keep it as simple as possible. If you're seeking to investigate, for example, intervention trade-offs, what needs to be endogenous to capture the effects of those interventions are key issues. So, any questions that I could answer about that? Yes, Ashish.
You had a slide which showed the progressive stages.
Yes.
And I had a question.
Yes.
There you go.
Yes.
The question was, if you have an existing system and you're trying to build a model of it.
Yes. Very common.
7 steps.
Yeah.
Feel very logical. But if you are trying to build a model first,
To design a
Okay.
system.
potential
Yeah.
system,
Yeah.
there would be some deviation from this.
I agree with you. For example, calibration. What are you going to calibrate against? What are you going to match model outputs against? You're still probably going to do problem conceptualization and mapping and model formulation to sort of characterize it. Model testing you'll still engage in terms of extreme value tests. How does the model behave when we assume very extreme values for things? Is it dimensionally consistent? Are we doing something similar, like adding a count of people to a amount of time or something like that? We do sensitivity analyses with the model to understand better what assumptions it's very sensitive. And a policy evaluation there would often involve investigating alternative design, for example, elements to see, the impacts on the outcomes of interest. For our health colleagues, that might involve, health service throughput and time in the system. Others might involve, health burden in terms of prevalent cases or incidence of some disease. In your case, it might involve service delivery metrics or quality of service metrics. But yes, you're right. The details of this, it's quite perceptive. The details of this will differ some. If you're anticipating using a model to build up a real-world system, rather than operating off of a sort of an understanding of a pre-existing system. Yeah. Good. Other questions? Yes, Kenny.
Yeah, can I obviously out my depth, but with the principle of incremental
Yes.
and the concepts of endogeneity and exogeneity,
Yes.
is the concept of building separate models and then stacking them together something which is recommended or to stay away from?
Yeah. That's a great question. So the question was, in this context of incremental model development, is it suggested to build models separately and then stack them together? I think that's good. I mean, one thing I should have said, and I stand to be corrected for having omitted it, is that over time, as a model evolves with learning, often what's going on is that you're moving things, say, from exogenous to endogenous or vice versa. You're taking things that were ignored and adding them into the model because you think it might in fact be sensitive to them. And so there's the model boundary changes. Jeff has a delightful video of pulsating amoebas that's worth a go. I mean, even if you like cat videos, they have little on it. I think he has it somewhere on his thumb drive. But the fact is that the boundary of our model adjusts with our learning. And in fact, as we'll see with any logic soon enough, sometimes you end up saying, oh, we characterize this in an aggregate way. Now we're going to turn that part into an agent-based characterization. Or you aggregate up. You say, look, it's, in the end, I don't think it's worth it. We'll aggregate back up. Jeff has some wonderful war stories about projects where, they went deeper, they constructed a more articulated model, and then towards the end they came back to a much more aggregated model that captures the nuggets, the essence of the issue, without trying to go into all sorts of details that get in the way of understanding. So you can really, huge difference between philosophies of different modelers, and particularly between system dynamics and agent-based modelers. With system dynamics, the strong goal of the model is to change mental models. In system dynamics, you very frequently see a focus of a model in changing how people think about the system. They want to help people make decisions in more judicious fashions, have a gut feel for what's going on so that they can behave more effectively under pressure, under novel situations. In agent-based modeling, unfortunately, that has not been a strong tradition. And it's more, get this model out to you, you learn from it, and there isn't this sense of bringing the stakeholder along with an understanding and sharpening our way of thinking about a situation. I view it as a historical difference. But I still haven't answered your question properly, and I'm keenly aware of it. So Kenny, what I will say is that stacking models is possible. We have had some absolutely amazing experiences within just the past 4 months in an amazing experience of model independent development and stacking in a series of hackathons. So my team, who stand formidably behind you, some of whom other troops are elsewhere. We've gotten them to engage on one problem, one sort of area over the span of 3 to 5 days. And the latest one, this primary care hackathon, it was awesome. So we had 4, and then eventually 5 teams, because one underwent, true to Jeff's fluctuating amoebas, it underwent mitosis and split. And then we had, so basically 4 or 5 teams developing models in parallel about the same basic area. And the models most of them were quite insightful. They captured interesting features of the situation. And each of them captured different areas differently, partly because of different modelers involved, partly because they were focused on somewhat different topics within that space, but overlapping topics. They had overlapped with other models. And that was an absolutely delightful learning opportunity. Our stakeholders came to supervise it. 3 of them flew out from the States, and one of them said he left with 6 pages of new insights into the problem domain from helping to supervise these models, because it was just bringing up these questions he had never thought about. The model outputs were stimulating new thinking, were challenging their ways of dividing it, and they were able to get collectively that power of many minds thinking about it in a way that really advanced thinking. I will tell you that we also build models that are modular. I was mentioning this to Ashish yesterday, that are modular in the sense that we sometimes slot in different implementations of a piece of the model. We swapped them out, a more detailed one for a less detailed one. So we have these kind of pluggable models. And you can do that with any logic with a bit of finesse. And the king of that, as with so many other things, is Winchell. He and a previous student of mine, Kurt, have both explored different avenues to pluggability in models. And what that allows you to do is to have different team members focusing on different pieces of the model, and then to combine them together in a very flexible way, but in a way that isn't welded together, but is rather, it's snappable. You stick it back in, and I don't know if that makes that sound in Australia, but in Canada it does here. And so you stick them together, and you can use them as a model, but if you don't need that extra level of detail, you take it away, and you stick something else in. So,
Lego?
yeah, it's like it's kind of a Legoized model, sure.
The smoking one makes me think of that a little bit, because you've got kind of multiple micro models almost
Yes.
within there in
Yeah.
terms of around the smoking behaviors and then heart disease and then how that leads to death and motivation. I mean, there's all those pieces
That's right.
that are within little models.
That's
Put
right.
it all together.
And Jeff and I have made many pitches thus far with limited success to any logic to support more fully this modular architecture where it would allow specification of a model library, which would have, might have a model for this model for smoking that's published in the literature. Narges is working on opioid addiction, this model for opioid addiction, this model for behavior change, the trans-theoretical model, stages of change. You might have, aspects of the health belief model captured in this, or aspects of heart disease as captured by Milton Weinstein's work at Harvard as captured, in an agent-based context. And you could plug those in, and sometimes you prefer one to the other, but you could reuse them instead of reinventing them from scratch. And I think it's a vision that can be accomplished. It's a vision that can be accomplished with our existing tools without the distant support of any logic from St. Petersburg. But it sure would be enhanced by support from the mothership. I'm not holding my breath, but Jeff and I are talking about maybe having another go at the persuasion. Because we have a much larger set of case studies and motivations, and from the data science side now, where so much of our modeling is focused and articulated with big data and with data science techniques like machine learning, we have yet more powerful needs for modularization that come in other areas. And it may be that any logic will bend its ear to our requests. But it wouldn't hurt to send them a few more encouragements. So yeah, thank you, and I agree with you that that model has a bit. Those different state charts, they almost beg for recognition as modules. But it's not just the state chart. The state chart is linked to statistics about the state chart. The state chart is linked to graphs about the state chart. State chart is linked to some event and variables that it frogs. And you put those together, and you have actually kind of natural models that cut across the whole any logic model. It's not just in the person; it's in main. And if you could put those in, you could get all at once this model of diabetes with these output indicators and intervention possibilities and variables that are used in the midst of it, and graphs and statistics and output to databases or files. It will be very powerful, yeah. And that remains the dream. But if any logic doesn't do it, we're going to do it. Someone's going to eat their lunch.
Call it the Jeff pile.
But speaking of eating lunch, I think there's food out there.
Yes, there's more snacks out here, more fresh coffee, more fresh tea, donuts,
Yeah.
fruit.
Thank you. Any comments? Any final questions, comments for now? I will just mention one final thing. Thank you, Christine. So, ladies and gentlemen, if I highlight here, okay, here's day one. If I were to go to participant resources, to go to the folder to which I've given you access, I would note that there's a model conceptualization folder here. This includes a number of exercises or a number of documents for you to think about. For example, I'm asking, okay, what are the primary goals of your model? Do you anticipate it being used to ask a question? What are some features of complex systems that are at issue? What levels of understanding or evidence are available? What things are endogenous, exogenous, or ignored for the first cut at your model? And similarly, there's a system mapping exercise where I challenge students to think of characterizing their model according to a framework that I like to call the O parties framework. And it stands for key outputs and outcomes, parameters that you need to capture, say for an agent, certain fixed characteristics of them. Actions, what are some actions they have to undertake, rules that govern those actions, and the state, the thing that might change as a result of those actions. Time, what's the sort of timeline you're interested in, the time horizon, any interventions to be considered, and what features in the environment, like their physical environment, aspects of their food environment or built environment, perhaps aspects of their social networks or contact networks, say needle sharing networks or sexual contact networks, might need to be thought about. And you might diagram these sort of things with state charts or causal links at an initial cut as just one way to sketch out the model. Don't get caught up in whether it's runnable yet, just sketching out what you're thinking about ways of describing the model. And we have a tool, which I may introduce to you, which is a web-based tool. It's kind of like Google Docs for drawing these diagrams, where many people can edit it at once and contribute to it by adding pieces in, which I'll see if I can show to you at some point. But for now, the food beckons, and tea and coffee with it. And so I encourage your escape. Okay? Thank you very much.
I was just going to mention
Yeah.
lecture slides for this
Yeah.
group. The theory articulation slide was in there.
Oh, it
I was
wasn't.
following along and I was like, oh, where's that slide? So that one, I think that's the only slide that I mentioned.
Oh, okay. So the one that I provided to you.
Yeah. That's
Okay, great. I'll put it there in a jiffy. Thank you so much.
And interesting, those exercises are helpful. And you probably know this because you mentioned this earlier, but it's similar, different, but a lot of similarities to developing the program logic model.
Yes.
What is your program? How do you
Exactly.
What are your outputs?
Exactly.
What you're expecting? How's that actually going to happen?
Agreed.
It's like, oh, this is cool. Yeah. Different, slightly different programs.
Very, very helpful. Yeah. Thank you for the comments. That's quite helpful.
No, no. All right.
Anyway, there's a figure. Environmental science.
It's awesome. It's awesome. I thought.
Imagine this, I was from Einstein Young.
Yeah.
We were going to build this group.
Yeah.
Since I have say about 10 people
Yeah. Yeah.
trained up to some extent.
Yeah.
Let's say EY is consulting with Royal Caribbean Cruise Lines. That assignment gets over, and we bring their principal architects who were on that in 2 days and let them brain dump
Yep.
as to what were the essentials of that business.
That's right.
And then get these 4 or 5 teams to
Yes.
sit and model, and now we've created a heritage
Yes.
of that experience.
That's right. No, and that's what we do. And the beauty of it, Ashish, one of the foremost beauties of it is I realized, because you have to understand, modeling is not easy, and I serve as kind of a hub to advise my groups. But they're quite mature, many of them. People at different levels, but many of them quite mature. They know AnyLogic very well. That's not the issue. The issue is model conception and design. It's not implementation. But what I realized is if I got them all going simultaneously on an issue, they can deliver much more variety and innovation than I can if I were to think about it for a couple of amount of time, actually. Because they can explore many lines of avenue and they can learn from each other. We have the groups see each other's work and try to learn from it. And they can also build each other's expertise. It's a bit like peer reviews too in software where you can have more experienced modelers building the understanding from less experienced modelers. And in short, it provides a great avenue for just within a very defined time, 5 days or something, just in a quantum level advancing your understanding of the issues. You're just much further along the line because there's just been this tremendous ferment of thinking on the parts of all these diverse teams working on different corners of it. And so you emerge out of there with this real asset, which is improved understanding, plus you get these models, which many of which are promising, and you might then combine. So Bryce, for example, combined, 2 models coming out of one of our hackathons from 2 different teams, and he combined them into a single model, which was very powerful. So these hackathons, in terms of being able to simultaneously explore different facets, elicit understanding, but also explore and identify promising and frankly sometimes not so promising avenues, right? You identify what you don't want to do, and you do it with such a small amount of time that then if you undertake a more industrial strength modeling project in that area, you have a much better terms of reference for what's needed. What's a fruitful avenue, what's not so fruitful. You have much better understanding coming out of it for how to advance in an informed way.
Do you see the result of such an exercise, let's say at the end of an assignment, if you were to build, this is essentially ensemble of modeling
That's
ideas.
exactly right. It's an ensemble. Yes,
built into
that's
a
exactly
model.
right.
But then turn this rascal around and turn it into a living model for the business,
Yeah.
where we now allow the CEOs and the CIOs to sit and do whatever scenarios.
Yes. Well, this is something that we've been working to with some of our health partners for sure, and to allow them to sort of explore with much greater rigor, possible impacts of possible strategies for intervening, et cetera, going forward. And I think it's a quite effective tool. It's something Jeff has thought about quite a bit, and it gets into some of these ideas which have been around at some level since the 80s or 90s, of decision support systems and strategic decision-making systems.
I've heard them talk about this term of digital twins.
Oh, right.
Creating a digital twin, let's say I had 39 large hospitals.
Right.
And I proposed, if I can build models for this, I could now have 39 digital twins of your hospitals and put together at a national operations center. Right. And see what's going on.
Yeah. And I think it's a great idea as long as there's ongoing learning. You don't want it to ossify around models that are
fixed.
You don't want to say, okay, this is our crystal ball, this is our model, it is gold standard, and from now on, this will be it. You actually need to learn where does it have gaps that need to be remedied, where is its aggregation level or oversimplification falling short, etc. There needs to be a learning process, and this gets into the whole principle of learning organizations, etc., which of course came out of much of Peter Senge's work at MIT and Sloan. So, I think viewing this as part of a learning ecosystem is very important. And that's what we've really built here. We built, the boot camps, internships, class projects, hackathons, the online materials, the incubators, more specialized boot camps. These are part of an ecosystem that are mutually reinforcing. And then
Keep
contracts.
doing that YouTube thing.
Yeah.
There are people like me who are benefiting from it.
This is valuable advice because I have some pressure on me to stop giving it away for free or whatever, but it's been my commitment to, get it out there. And in my own view, it probably only attracts people, so
Some of my videos
Yeah.
I go and like, this has been out there for 5 years and only 76 people have viewed it. What's wrong?
well, if you can help more people see it, that would be great. Talk to Jeff about that because we're both in this, and Christine as well, my secretary, my colleague, really. Yeah.
I just wanted to let you know that I have to be there tomorrow.
Okay.
Not just like an hour.
Okay. Okay. Thanks a bunch.
Really nobody ever goes back to these unless you're making it to very seldom you get lit like some viral disease or whatever. Usually by then they've been vaccinated and this is a one-time shot for some days. This is really the first Yep. There. So I mean those cases yeah, and so we have to work on your soldiers recovered, and there's and whether they're actually infectious or not, who knows? Maybe they are, maybe they're not. A lot of those cats are just rumors, like they're just. Yeah, they'll die. Well, we need to tone that down a little bit apparently, but you could have split off here to have you'd have cats that would die from here, and you'd have cats that would go from here, depending on how many times. We might be able to integrate that into. I would. Actually, no, because the seasonality is taken care of by when cats are coming into the model, right? That takes care of it for us, so we don't even have to get that complicated. But I will maybe I'll try and save this. I mean, it's not perfect, but I guess the reason I wanted to show you is when we've talked about it before, I always thought, this is going to be impossible to get right? For us to come up with a curve that looks like the curve is going to be really hard to do that. It's going to take a long time. It's going to be really complicated. And it took about 10 minutes to get something that's close. I mean, you have to get it closer, but it took about 10 minutes to sort of get in the rough ballpark of where we need to be. So that would be like super without hopefully adding too much complexity. Like I said, just be for respiratory disease, not for anything else. But one of the criticisms is going to be that our respiratory disease is just not. Second treatment is responsive to AMR. Third treatment is, but not the first treatment isn't really. It doesn't even. It's not super responsive right now to other things that are going very well. And it would be nice because that's where you can, if you want to precondition and you want to look at other things. That's where having this flexibility would be really cool because then you just. We've got a precondition kind of chaos where we just stick them in, this vehicle. Yeah. Yes. Yeah. And that's, and you can still use the intervention data to inform this and to calibrate this. but we don't, we will need less data for this approach. We don't need perfect data for this, we just need, rough ballpark data. Oh, yeah, just in the publications. Anyway, I was just, I guess the reason I wanted to show you, I was just surprised that it actually cooperated reasonably well without having to scream and yell at it. Okay, take a break, I'm gonna mention the Washington or whatever, but if you wanna, I don't know, would you, we don't really need to scope our model because we've already kind of done that. So, there's something you wanna, if you wanna work on that one, or if you wanna work on if you wanna look at the other one and try.
I can look at the other one, this one is really,
Yeah.
I think everything you talked about, I think so.
It's too, it's, I know you have to go and I mean, that's important, but it's just too bad you didn't reach it from the beginning, because this would be a very crucial audience.
Can I consult with this gentleman for
I think she was just joking, and I wouldn't recommend using that unless she insists.
I know.
Okay, it's not just me.
Oh, it's freezing.
I'm sitting on my hair, I just got bent.
I had to run. I was had to meet a friend of mine, so I was running late because I didn't realize we were going to as late as we did yesterday. But I was like, I have to stop in my hotel room and roll my feet because they're going to start cramping, so it's freezing off. I just wanted to put my feet under hot water for a while before I could like go out.
Yeah, I'm gonna check what we have down. I think
Thank
we
you.
have a
I
couple.
appreciate it. Because my friend said,
Couple down.
It's just a place. I was like, it just holds a cold in. It doesn't matter. I was like running around sometime with my friend.
Okay.
A really good reason for this, given the amount of technology in these rooms. But many of us are freezing.
Oh, really?
Yes.
Okay.
And it's not just the girls.
Yeah, no. That's really good understanding, and
Because we have to swap our hands to keep them warm.
whoa, wow. Okay, let me see if I can get someone looking into this. Thank you very much.
Whether it's the controls are accessible is another question.
Is anyone not cold? It's probably really cold. Yeah.
And I usually just assume it's just me, so.
No.
I was like, you just really cool.
Well, I like to watch them because she actually gets dressed as the day goes on.
No, I.
Bring a blanket.
I love that. Or play with it. Plan for the rest of the afternoon.
Yeah.
This later?
Yeah, so I'm going to be announcing things, but basically project times now, and we're going to be having some case studies, which I'm going to be discussing as well.
Any more lecture stuff today?
I think we'll go with the projects and the case studies, unless people run out of steam, in which case might do something at the end. Wade?
Yes.
Would you be, some just shuffling things around here, but so for this one,
Yeah,
are you up for that?
yeah, I can do that.
Is that
You wanna do
okay?
it now,
Uh,
or this afternoon?
yeah, I think so.
Because we missed that in the morning.
Right, and we this in the afternoon,
Yeah.
but which is I think about the time for that. So, are you okay doing that?
Yes?
Okay, that would be great. Okay. Okay. Sure. So I'll.
So, are we gonna start that imminently? Should I pack up? and
Yeah,
head
if
over
we
to
could,
the
if
other room?
we could do that. Ladies and gentlemen, I think we will get the projects underway. What I would suggest is in the spreadsheet, to which many of you have access, we have different rooms and different teams. And so, Kenny, your project, I thought we'd show in 371. If one of the TAs could help show him where 371 is, Jason, and I think you and Narges are down for this. And Rifat, if you'd like to go along, or would you prefer? Rifat, do you want to be on a different one?
No, I'm fine.
Sorry, it was 371?
Yeah, 371. Okay. Okay. Bryce, you and Megan, if you could go to 341, that would be great.
Or maybe they're just,
Megan Mueller? Mueller or Mueller? Mueller, thank you. Wade and Megan Mistay. Oh, Wade is gonna, yeah, that's right. Wade is gonna be giving, so Wade is gonna give a case study if anyone is interested. He's gonna give a case study on chickenpox and shingles vaccination and an ABM to evaluate the effects of immunization for both chickenpox and separately shingles. So this is varicella zoster virus. If anyone's interested, he's going to be an S386, and you're welcome to take that in. Maybe what I'll do is, maybe I'll have him come here. In fact, and then he could just deliver it from here. That seems like an easier thing.
Is he gonna record?
Yeah, he could record it here. That's the thing. Jeff, do you think you might be able to go? Yeah, down at the end, 386. Yeah, and that would actually free up that room. So Terry, Iden is outside. Do you know Iden?
Maybe.
Could you get? Yeah, thank you, Tina. Iden, so Terry is up here. What I would suggest is, so we've just freed up S386. If you could maybe consider going there. And for today, you could use that room. Is that okay? Okay. Sorry? There is a computer there. There's an instructor station there. Yeah. You might need my key to get in there. I don't know. Yeah. Okay. Ashish Winchell was going to come talk with you. I'll let him know.
Okay.
Okay. Enter the dragon. That's great. So you're okay with doing it here?
Yes.
Okay, awesome. Now, Erica and Claire.
Well, we thought we were going to go with number 4, but
Yeah.
you said that was...
Well, is it possible you could join 4 and then we could have a TA on that?
Yeah, that's fine.
And then it will let our TAs stretch around?
That's fine.
Okay, awesome. Now, that's going to be in 341. I think that's okay, but I'm going to give you a special TA, a separate TA. Okay? I'm going to give Tina as a TA. And Wade, you'll be working with Megan McStay here after this.
She's seated there, or?
No.
This is Megan.
This Megan.
That's Megan.
Yeah.
All right.
Yeah. So after your presentation, you can move over there. Okay, great.
Is for the Winchell around?
Yeah, I'm gonna get Winchell. He's just.
He went that way. He went into the big room.
Yeah. You want key? Sure. Right. Let's go. And Wade, I'll get the recording set up.
Okay.
Oh, Tina? Oh, no. So I was hoping that you could help Erica and Megan here.
Okay.
And they're doing a project that is also of interest to Megan Mueller. Okay? She's in 341.
Okay.
If you need more space, just let me know.
Yeah,
Get you a bigger room. Okay?
Yeah.
Thank you. I'm trying to find out this thing about the cold too. But everybody
Can
wants
just
to-
bring more clothes.
Hi, Christine. So a number of participants are reporting being very cold in this room. And I don't know if there's anything that can be done, at least transiently, to lessen the, to raise the temperature a bit. But thanks a ton. Thanks greatly. The other thing, Christine, is that remember that issue that Smith was trying to fix yesterday about logging me out of that computer automatically?
Yeah.
That's still going on.
Still logging in on, okay.
Yeah.
Well, ICT is going to be coming over tomorrow, so we can walk through all of that.
Okay, yeah, except I don't think ICT is involved with this part, so I think that was Ralph.
Yeah, it probably will be, and I will let Smith know that he needs to work on that as well.
Great, thanks a ton.
Okay.
Sorry for the trouble.
Not a
Bye-bye.
problem. Bye-bye.
Okay, Wade. So Wade is going to give a talk on chicken pox and shingles, which are two different conditions caused by a common virus, the varicella zoster virus, VZV. And he's kindly offered to give this second case study for the sake of this group. So Wade, I'm going to just start this up. Do you have your thing on? Okay, great. Okay.
Check, check.
Okay, wait, and there we go. Good. Take it forward from here.
All right, good afternoon. I was introduced yesterday. My name is Wade. I'm going to talk about a different model I worked on chicken pox. This one has actually recently been published in a journal. So this one, the team was Dr. Alexander Doroshenko from Alberta Health, who Dr. Osgood has collaborated with multiple times now.
And as a veteran at the boot camp, multiple times.
Yeah.
Yeah.
And Dr. Marwa Farag was from the School of Public Health, and Dr. Osgood. And the students were Ellen Rafferty, who was a PhD student, now graduated in the School of Public Health, and I was the computer guy. This work on this started when I was a undergraduate summer student in Professor Osgood's lab, and then continued into my master's degree and was published this June. And then, of course, the King Winchell, who has touched many projects within this lab and is a key member. And then these folks, I don't know them, but they this actually started its life as a class project in Professor Osgood's simulation class with Ellen and these two gentlemen working on it. So it's changed hands.
Actually, one is a woman.
Oh, I'm sorry.
Yeah, Nazifa is a woman. Yeah.
Okay, I apologize.
No.
I've never met them face to face. So key features in this model, it's got a user-defined network of 500,000 agents. An open population, meaning people are born and die and migrate. There was a preferential contact age for children, different connection ranges for each disease, a contact matrix, a bimodal population density, And I'll say more about each of these. And we configured it for a headless run, which I'll talk about a bit about. Things have changed on that front since I first gave this talk, but we can discuss that. So that was, we ran it on multiple PCs in this very lab, actually. So here's the state chart for the disease. Chickenpox and shingles are two diseases caused by the same virus. It's the varicella zoster virus. Chickenpox is childhood disease, as you probably know, and then the virus remains in your body, and it can reactivate as shingles later in life. So what we're representing here, maybe a little hard to read on the screen, this state is for maternal antibodies, so for about 6 months after a child is born, approximately, they're covered by their antibodies they receive from their mother, then they become susceptible. On exposure, a person can become infected with chickenpox, and then this is infected, not infectious chickenpox, so they're in the red infected state. They can also spread it to other people. And then they move into this recovered chickenpox state. And I'm going to back up here. This stuff here, protected 1 and protected 2 represent the 2-stage vaccination for chickenpox. And if you've received 1 dose of the vaccine and are exposed, you have a possibility of getting a breakthrough infection. And then you get a weaker version of the chickenpox infection, which then progresses in the same way as the regular disease. Within this light blue recovered state, we represent something called boosting. So if an agent that is recovered from chickenpox encounters an infected agent with chickenpox, they can receive a boost to their immune system, and that won't make them sick, but it actually boosts their immune level. Now, this is